Hello, welcome to Know About History channel. Hope you like it.
The science of reading minefields from the sky is a discipline born from the desperate necessity of modern warfare and the enduring tragedy of its aftermath, representing a sophisticated synthesis of physics, chemistry, biology, and historical military doctrine. To understand how we detect buried death from thousands of feet in the air, one must first appreciate the inherent nature of the landmine as a weapon of temporal persistence. Unlike a bullet or a shell, a landmine is a dormant agent of kinetic energy, designed to wait for years or even decades. The historical evolution of detecting these hidden threats from an aerial perspective began in earnest during the Second World War, specifically in the North African theater. Generals like Erwin Rommel and Bernard Montgomery transformed the desert into a canvas of Devil's Gardens, where millions of anti-tank and anti-personnel mines were laid to channelize enemy movements. Early aerial reconnaissance pilots, flying high-speed aircraft equipped with high-resolution cameras, began to notice that the act of burying a mine left a distinct chronological scar on the landscape. When soil is disturbed, its natural compaction is broken, and the deeper, often moister or differently mineralized earth is brought to the surface. This creates a change in the soil's albedo, its reflective capacity. Even after a minefield is camouflaged, the spectral signature of the disturbed earth remains different from the surrounding undisturbed crust for a significant period. During the 1940s, analysts used stereoscopic imagery, viewing two overlapping photos through a specialized lens to create a three-dimensional model of the ground. This allowed them to identify the subtle depressions or mounds that indicated a freshly laid mine row. This was the primitive beginning of what would become a highly digitized and multispectral field of study. As the Cold War progressed, the complexity of mine warfare increased, and so did the science of aerial detection. The Vietnam War served as a crucial turning point, particularly with the American implementation of Operation Igloo White. This was an attempt to create a sensor-based battlefield along the Ho Chi Minh Trail. While many of the sensors were dropped to the ground to detect acoustic or seismic vibrations, the aerial observation component began to experiment with thermal infrared detection. The physics behind this is grounded in the concept of thermal inertia. Every material has a specific capacity to absorb, store, and release heat. A landmine, whether encased in metal or plastic, has a different density and thermal conductivity than the soil in which it is buried. During the daylight hours, the sun heats the surface of the earth. A buried object creates a thermal bridge, or a thermal barrier, depending on its depth and material composition. As the sun sets and the earth begins to cool, the area of ground directly above a mine will cool at a different rate than the surrounding soil. This creates a thermal halo that can be captured by infrared sensors. In the arid environments of the Middle East or the scorched plains of Africa, this temperature differential is often enough to reveal the exact geometry of a minefield from a low-flying aircraft or drone. The science of reading these halos requires an intimate knowledge of local geology, as different soil types, sand, clay, or loam, will produce different thermal signatures, sometimes masking the presence of the mine or creating false positives from buried rocks or metallic debris. The transition from traditional photography to hyperspectral and multispectral imaging has revolutionized the field in the 21st century. While the human eye sees only a tiny sliver of the electromagnetic spectrum, modern aerial sensors can divide light into hundreds of narrow bands. This allows scientists to look for chemical fingerprints from the sky. Landmines are not perfectly sealed containers. Over time, the explosive filler, typically TNT, RDX, or PETN, slowly leaks into the surrounding environment. These chemicals are highly toxic and affect the physiology of the vegetation growing above them. This is the field of biogeochemical remote sensing. When a plant absorbs these trace explosives through its root system, its internal cellular structure undergoes stress. This stress manifests in a phenomenon known as the red edge shift. In healthy plants, there is a sharp increase in reflectance between the red and near-infrared wavelengths. In plants stressed by the presence of explosive compounds, this shift occurs at a different wavelength. From a satellite or a high-altitude drone, a historian or deminer can map an entire minefield by simply looking for patches of grass that are unhealthy in a very specific, chemically induced way. This method is particularly effective in dense, inaccessible areas like the jungles of Cambodia or the forests of the Balkans, where ground-level demining is slow and perilous. Another pillar of this science is the use of synthetic aperture radar, SAR. Unlike optical sensors, which are passive and rely on sunlight, SAR is an active sensor that emits microwave pulses and measures the return signal. SAR is unique because it can penetrate cloud cover, smoke, and even the upper layers of dry soil or foliage. The historical value of SAR lies in its ability to detect man-made regularity. Nature rarely creates perfect lines, circles, or grids. Military minefields, however, are almost always laid in specific tactical patterns to ensure maximum coverage and ease of recording for the friendly forces who might one day need to remove them. SAR can identify these geometric anomalies amidst the chaotic texture of the natural world. In recent conflicts, such as the ongoing war in Ukraine, SAR has been instrumental in mapping the massive defensive belts laid across the steppes. By analyzing the surface roughness and the dielectric properties of the ground, radar can highlight the linear scars of anti-tank trenches and the associated mine belts that protect them. This data is then cross-referenced with historical military maps and satellite archives to build a comprehensive picture of the threat landscape. Furthermore, the rise of artificial intelligence and machine learning has provided the brain for these aerial eyes. The volume of data generated by modern aerial surveys is staggering, petabytes of high-resolution imagery that no human team could analyze in a lifetime. Computer vision algorithms are now trained on signature libraries of known mine types and minefield patterns. These AI systems can scan thousands of square kilometers of aerial imagery to identify indicators of mining. These indicators are not always the mines themselves but the infrastructure of death that surrounds them. For example, the presence of certain types of perimeter fencing, the specific way a road has been cratered and then bypassed, or the remains of specialized mine-laying vehicles. In the Falkland Islands, researchers used aerial drones to map the movement of peat and sand over decades, using AI to predict where the wandering mines might have shifted due to geological erosion and weather patterns. This historical spatial analysis allows for a more dynamic understanding of how a minefield lives and changes over time. The science also encompasses LiDAR, light detection and ranging, which uses laser pulses to create ultra-high-resolution three-dimensional maps of the terrain. LiDAR is particularly effective at stripping away vegetation. In a process known as digital deforestation, analysts can use LiDAR data to see the ground surface beneath a thick canopy. This has been a game-changer for identifying the historical remnants of old wars. In the dense jungles of Southeast Asia, LiDAR has revealed the pockmarked landscapes of B-52 carpet bombing and the hidden trench lines of the Khmer Rouge, which are almost always accompanied by extensive minefields. By identifying the micro-topography of the ground, the tiny depressions where a mine was buried or the low-relief mounds of unexploded ordnance, LiDAR provides a structural blueprint of the danger zones that would otherwise be invisible to the naked eye. From a historical perspective, reading minefields from the sky is also an act of forensic archaeology. Every minefield tells a story of a specific moment in time, a commander's fear, a strategic gamble, or a desperate retreat. By analyzing the patterns of these fields, historians can reconstruct the flow of battles that occurred decades ago. In the deserts of Libya, the World War II signatures are still visible, preserved by the arid climate. Aerial analysis shows how the minefields were used to funnel the panzer divisions into killing zones. In the Balkans, aerial surveys help track how minefields were used during the ethnic conflicts of the 1990s, often laid without maps as a tool of terror against returning refugees. The ability to read these signs from the sky is not just a technical achievement, it is a vital component of humanitarian efforts to restore the land to its people. It bridges the gap between the violent past and a safe future, allowing for the systematic clearance of land that has been locked by the presence of explosives. The future of this science lies in multi-sensor fusion, where data from SAR, thermal, hyperspectral, and LiDAR all layered onto a single digital map. This holistic approach minimizes false positives and provides a high-confidence assessment of the ground. It also involves the use of biological drones, training bees or using genetically modified plants that change color in the presence of TNT vapor, which can then be spotted by aerial cameras. This intersection of high technology and natural biology represents the next frontier in our ability to cleanse the Earth of its hidden scars. As we refine our ability to read the Earth from the heavens, we move closer to a world where the perfect soldier of the minefield is finally defeated, not by force, but by the relentless application of human ingenuity and scientific observation. The sky, once only a vantage point for the delivery of death, has become the primary tool for its discovery and removal, ensuring that the history of a land is no longer written in the blood of those who walk upon it. The historical depth of this aerial analysis also requires a look at the specific materials used in mine construction throughout the decades. In the early 20th century, most mines were metallic, making them relatively easy to find with basic electromagnetic sensors. However, the move toward minimum metal or entirely plastic mines during the late Cold War, such as the Italian-made VS-50 or the Soviet PFM-1 butterfly mine, forced a radical shift in aerial detection science. Because these mines could not be detected by traditional metal detectors, the reliance on optical and thermal anomalies became paramount. The PFM-1, in particular, presented a unique challenge. Being air-dropped by the thousands, they did not follow the neat geometric patterns of hand-laid fields. Instead, they created scatterable minefields that looked like a random distribution of debris. Reading these from the sky requires a different statistical approach, looking for density clusters and the specific aerodynamic signatures of how these mines land and settle into the grass. Analysts must account for the self-burial process, where wind, rain, and gravity gradually hide these small, green or brown plastic objects from view. Moreover, the geological context is inseparable from the aerial science. For instance, in the high-altitude deserts of Afghanistan, the soil is rich in magnetic minerals that can interfere with certain types of sensors. Aerial analysts must calibrate their instruments to the specific mineralogy of the region. This is where the historian-analyst role becomes crucial, as they must synthesize the military history of the area, knowing which factions used which types of mines, with the geological data to filter out the noise. In the wetlands of Angola, the challenge is different. The high moisture content of the soil changes the way heat is conducted, often masking the thermal signature of buried mines. Here, the focus shifts to the use of multi-band radar that can distinguish between the dielectric constant of water-saturated soil and the dry air gap often found inside a buried mine casing. The psychological dimension of minefield reading also plays a role in aerial reconnaissance. The mere presence of a drone or a surveillance aircraft can sometimes be used to flush out information. In some post-conflict scenarios, deminers have used the aerial perspective to identify human-worn paths. Humans are creatures of habit, and even in a heavily mined area, locals will often find a safe path. From the sky, these paths appear as thin, compacted lines of soil that deviate from the most direct route to avoid known danger zones. By mapping these desire lines, aerial analysts can infer the boundaries of the minefield without ever seeing a single mine. This is a form of behavioral mapping, using the collective memory of the local population, as etched into the ground, to supplement the technological data. The evolution of sensors has also led to the development of gas-sensing drones, which carry miniature mass spectrometers or electronic noses. These devices can detect the parts per billion cent of explosive molecules off-gassing from the ground. While wind patterns make this difficult, the aerial perspective allows for the mapping of vapor plumes back to their source. This technique is particularly useful for finding deep-buried, large anti-tank mines or caches of unexploded ordnance that have been buried by time or intentional concealment. It is a form of atmospheric archaeology, where the air itself holds the clues to the dangers buried beneath. In the final analysis, the science of reading minefields from the sky is a testament to the fact that no human action is without a footprint. Whether it is a physical disturbance of the soil, a chemical change in a blade of grass, or a subtle thermal anomaly, the act of planting a mine leaves a permanent mark on the world. Our ability to see these marks from the sky is a powerful tool for peace. It allows us to map the extent of the problem with a speed and safety that was once unimaginable. As satellite technology becomes more democratized and drone sensors become more affordable, the secret of the minefield is being stripped away. The historian looks at these aerial maps and sees the strategic lines of past wars. The scientist sees a complex puzzle of electromagnetic signatures, and the humanitarian sees a path toward a cleared and productive future. The synthesis of these perspectives is what makes the aerial study of minefields one of the most vital and fascinating fields of modern forensic science. It is a constant battle against time and the elements, a quest to reveal the invisible and to ensure that the perfect soldier is finally brought to light and neutralized. Through the lens of a satellite or the sensor of a drone, we are not just looking at the ground. We are looking through the layers of history to find the truth of what lies beneath, ensuring that the legacy of war does not continue to claim lives long after the guns have fallen silent. This ongoing effort requires constant vigilance, as the signatures of these fields continue to fade and shift, demanding ever more sensitive instruments and more clever algorithms to keep the world safe from the hidden ghosts of its own violent past. In the context of modern geopolitical shifts, the science of aerial demining has also become a tool of international law and accountability. By using time series satellite imagery, looking at images of the same location over several months or years, historians can pinpoint exactly when a minefield was laid. This is crucial for identifying which military force is responsible for new mining in violation of international treaties like the Ottawa Convention. The sky does not just reveal where the mines are, it reveals when they arrived. This temporal dimension adds a layer of forensic responsibility to the science. For example, by comparing high-resolution imagery from before and after a specific offensive, analysts can document the creation of a minefield, providing evidence for future war crimes tribunals or reparations claims. This use of aerial data transforms the reading of a minefield from a purely technical task into a powerful instrument of justice. The global database of minefield signatures is also growing. Organizations are now using crowdsourced aerial data, where imagery from various sources is fed into a global model to improve the accuracy of detection in different biomes. A signature in the frozen tundra of a northern border will look vastly different from a signature in the red clay of Southeast Asia or the sandy loam of the Middle East. By cataloging these variations, scientists are creating a global atlas of minefields, an ambitious project that aims to provide a baseline for demining efforts worldwide. This atlas relies on the persistent gaze of satellite constellations that orbit the Earth every few hours, providing a level of surveillance that makes it increasingly difficult for any actor to lay mines in secret. As we look toward the 2030s and beyond, the integration of quantum sensors into aerial platforms holds the promise of even greater breakthroughs. Quantum gravimeters, for instance, could theoretically detect the tiny mass deficit created by the void of a mine casing underground, regardless of whether it is made of metal, plastic, or wood. This would bypass the limitations of thermal and electromagnetic sensors entirely, allowing for a pure, physical detection of the object itself. While still in the experimental phase, such technology would represent the ultimate evolution of the science, a way to see through the Earth as if it were glass. Until then, the rigorous analysis of light, heat, chemical stress, and historical patterns remains our best defense against the hidden threat. The work of reading minefields from the sky is a never-ending process of refinement, a journey from the blurry photographs of the 1940s to the multidimensional digital models of today, all driven by the simple, profound goal of making the world a safer place to walk. Each pixel of data, each thermal anomaly, and each stressed leaf is a piece of a larger puzzle that, when solved, saves a life. This is the true heart of the science, using the highest technology to protect the most basic human right, the right to move across the Earth without fear. The meticulous nature of this work also extends to the archaeology of the sensor. Historians must understand the limitations of the technology used in different eras to correctly interpret old records. A hot spot on a 1970s infrared scan might be a mine, or it might be a technical artifact of a primitive sensor. Modern analysts must often reprocess historical aerial data using contemporary algorithms to uncover secrets that were missed at the time. This historical resensing has led to the discovery of forgotten minefields in places like the Golan Heights or the borders of former Soviet republics. It is a reminder that the data we collect today will be the historical record of tomorrow, and the clarity with which we read the ground now will determine the safety of future generations. The science of reading minefields from the sky is, therefore, a bridge across time, connecting the tactical decisions of the past with the humanitarian imperatives of the present and the technological possibilities of the future. It is a discipline that demands the highest level of accuracy and the deepest level of commitment, for in this field, the cost of a misreading is measured in human lives. The sky is no longer just a place to watch the world, it is a place to heal it. The complexity of these minefield signatures is further compounded by the environmental changes that occur over decades. In many parts of the world, climate change is altering the very ground we are trying to read. Rising sea levels in coastal regions can submerge minefields, while increased desertification can bury them under meters of shifting sand. Aerial science must adapt to these dynamic terrains. For instance, in the flooded plains of South Sudan, researchers are using bathymetric lidar, a type of laser that can penetrate water, to search for submerged ordnance. In the shifting dunes of the Sahara, they use temporal change detection, comparing satellite images over several years to track how sand dunes move and reveal, or hide, the mine belts underneath. This constant state of flux means that a minefield is never a static object. It is a living, shifting threat that requires a persistent aerial gaze to manage. Furthermore, the social history of the land can be read from the sky. When a minefield is present, it creates a no man's land, where nature often reclaims the territory. These accidental nature reserves have a distinct ecological signature. From the air, one can see where the forest has grown thicker or where the grass is taller because no livestock have grazed there for 30 years. This reclaimed wildness is a primary indicator for aerial analysts. In the Korean Demilitarized Zone, DMZ, the lack of human interference has created a unique ecological corridor that is visible from space as a ribbon of deep green crossing the peninsula. Within this green ribbon, the scars of the original minefields are still there, hidden under the canopy but detectable through the structural analysis of the forest height and density. The sky tells us not only where the danger is but how the Earth has responded to its forced isolation. The economic impact of this science is also profound. By providing high-confidence maps of mine-free areas, aerial surveys allow for the rapid return of land to agricultural use without the need for slow, expensive ground clearance of every single square meter. In post-conflict nations, this land release process is essential for economic recovery. The ability to read the sky and certify a field as safe based on multispectral data and historical lack of activity is a major focus of current humanitarian research. It reduces the economic paralysis that minefields impose on a country, turning dead land back into living land through the power of remote sensing. In conclusion, the science of reading minefields from the sky is an intricate tapestry of many threads. It is the physics of light and heat, the chemistry of explosives and plants, the history of military tactics and human suffering, and the mathematics of artificial intelligence. It is a field that requires the cold objectivity of a scientist and the deep empathy of a humanitarian. As we refine these techniques, we are not just discovering mines. We are uncovering the hidden history of our world and working to ensure that the future is not dictated by the debris of our past. Every flight of a drone, every orbit of a satellite, and every line of code written to detect a thermal halo is a step toward a world where the ground is once again a place of growth and life, rather than a hidden minefield of death. The sky, in its vast and silent witness, has become our greatest ally in this endeavor, providing the perspective needed to see the invisible and the wisdom needed to heal the Earth. The work continues, pixel by pixel, wavelength by wavelength, until the last, perfect soldier is found and the landscape is finally free. This is the legacy of the science, a clearer vision for a safer world, where the view from above brings peace to those below. The depth of this analytical journey also brings us to the importance of ground truthing. No matter how advanced the satellite or drone sensor, the science remains incomplete without the physical verification on the Earth's surface. This is a feedback loop. The aerial data informs the deminers where to look, and the findings of the deminers are fed back into the AI models to train the sensors to be more accurate. This relationship between the sky and the soil is the heartbeat of modern mine action. It is a dialogue between the macro and the micro. In the future, we may see swarm intelligence, where hundreds of small, low-cost drones coordinate with each other, using different sensors to triangulate a threat. One drone might detect a thermal anomaly, another would move in to perform a hyperspectral scan of the vegetation, and a third would use a specialized sensor to sniff for explosive vapors. This multi-layered, automated approach would mimic the way a human team works, but with a speed and safety factor that is orders of magnitude higher. Moreover, the ethics of the sky is an emerging subfield. As these surveillance tools become more powerful, we must ensure they are used for humanitarian purposes and not for further conflict. The same technology that finds a mine can be used to target an individual. Therefore, the transparency of the data is vital. Open-source platforms that share satellite imagery of mine-affected areas allow for a global eyes approach, where researchers from all over the world can contribute to the mapping effort. This democratization of the science is a powerful check against the misuse of the technology. It turns the view from above into a shared human resource, a collective effort to clean up the planet. Ultimately, the science of reading minefields from the sky is a story of human resilience. It is our response to a weapon that was designed to be unfindable and unbeatable. By using every tool in our scientific arsenal, from the subatomic properties of molecules to the orbital mechanics of satellites, we are proving that there is no secret the Earth can keep forever. The Devil's Gardens are being mapped, the butterfly mines are being tracked, and the invisible war is being made visible. This is a triumph of light over shadow, of knowledge over fear, and of the future over the past. As we continue to look down from the heavens, we do so with the hope that one day, the only things we will need to read from the sky are the patterns of our cities, the health of our forests, and the peaceful movements of a world at rest. The mission to clear the minefields is far from over, but the science of the sky has given us the map we need to finish the journey. Each day, the resolution gets higher, the algorithms get smarter, and the world gets a little bit safer, proving that even the most hidden scars of history can be healed if we only have the vision to see them. This process of visual and scientific exorcism of the land is one of the great quiet victories of our age, a testament to what can be achieved when we turn our eyes, and our technology, toward the service of life.